Howdy, and welcome to week 5, where we're going to discuss Monte Carlo simulation as our technology of choice. Do you remember the movie about the brilliant mathematician and how his mind saw things? There was a scene where he's walking into a bar and he sees this graphics of how people should interact. It's called game theory, and we use a lot of game theory when we're talking about solving complex problems that we can't do with algorithms. And by that I mean we can define algorithms to look at the problems, but there's no way to actually solve them. So we've run into a lot of occasions in life and situations where we look at how we approach the problem and we come up with methods of how to approach the problem, but we don't have a 100% solution. So as I record this, I sit in my office in Galveston. So we know that there's certain predictable paths in hurricanes, and we attach probabilities. No one says specifically, this hurricane is going to hit at this time with these consequences. It's always a probability. So you'll see these spaghetti models where the European model says it goes this way, something else goes this way, something else goes this way. It's all based on statistics. This is a branch of statistics called game theory, and one of the most prevalent technologies is Monte Carlo simulation, which we're going to talk about today. Now, the problem with Monte Carlo simulation is a lot of times you really have to dig and get the data. But that's sometimes more doable than not. As with any of these technologies we talk about, there's certain circumstances where they work better. So it's basically comes from the probabilistic nature. So if you go gambling in Vegas or someplace, you play a roulette, slot, dice machine, the house always wins, right? The probabilities are stacked that way. But when you pull the arm or when you do this or do that, you're playing in a game of probabilities. What's more likely than not? What's the probability? You've got 52 cards. What's the probability you're going to get the ace of spades to show up? What's the probability you're going to get this? What is the probability of a certain hand? So that's actually where this came from, Monte Carlo simulation. It's a technique to model processes that can't be easily predicted because the randomness of so many contributing factors. So let me give you an example. Several years ago, early 2000s, I ran U.S. operations for an Israeli-owned company. And we did reliability, availability, and maintainability of high-dollar assets. A good example would be jet engines. Cost a lot. If one of them has a spare part or has broken down or something, it can cost the airlines a lot or the military a lot, depending on where that jet engine is. Same thing in a power utility. They have these large motors, which are basically the same design and same basic workings of a jet engine. It's just that they're latched in our utility. And these are hundreds of thousands of dollars of investment, and they have to be able to predict the reliability. Are they going to be there? Are they going to be reliable? The availability, are we going to have enough working to provide whatever, power or a number of planes in the air? And the maintainability, how do we best maintain them? And this is a very complicated technique. This particular technology used Monte Carlo simulation because it basically put probabilities on all the parts, and then it ran simulations. You may run 100,000 simulations, not you personally, the computer, and say, here's the probability this is going to happen. As with any probability, you always have a standard deviation. So again, Monte Carlo simulation goes and runs, by simulation it means hundreds of thousands of throwing the dice. So think of it that way. I throw the dice 100 times. What's the probability the number 6 comes up, right? Well, how many sides are on a dice? So you figure it's that probability that each of the sides are going to come up an equal number of times. But you could throw it 10 times and have the 6 come up. Unlikely, but it could happen. Or just think of a coin, flipping it 100 times. We think 50 times head, 50 times tails. But we might flip it and the first 7 times it comes up heads. Over the long term, it's 50-50. But over the short term, it may not be 50-50. Now think about if you're throwing a lot of coins mixed in with dices, mixed in with all this other stuff, that all have different probabilities. The best example of how to use this, or to make this relevant to you, is in the financial services. You don't see these ads that much anymore, but there used to be an ad. If you put so much away in your 401k or your retirement plan and you assume an average 10% return for 20 years, which frankly in this day and age would be a great assumption. But that average 10% could be 0% for 10 years, followed by 20%, which is going to be a lot less money than if you got 20% the first 10 years, followed by 0%. Or 8% for so many years and then 12% or whatever to come up with that average. The results are wildly different. So I'll be honest with you. I started to build a spreadsheet to build a demonstration, and then I found one on YouTube. So that's the one I'm going to give you to look at. I'm also going to tell you that if you want to do a Monte Carlo simulation, guess what? You have a free tool to do it, and you'll see this in the video as well. It calculates it many times, generates useful information from the results. You've got it. You don't have to pay any extra money. Turns out it's with your basic Excel functionality. So thank you for your time. There's going to be 2 videos plus the YouTube videos, so 3 videos this week. Thank you.